I had a poor connection, so I have to restart this again. Sorry for uploading so many different videos. And I'm not sure if I could restore the note for like the last 20 minutes video, because some of my file cannot be opened again. Anyway, so I hope I can successfully save this one. So the for an n-way set associative cache, so for the previous example, suppose we're trying to make a cache, a direct map cache, and then you have 8 different sets, and the capacity of the cache is not changed. So again, we still are using the same capacity. So we still have 8 words at the biggest capacity as the capacity of the cache. And instead of designing the cache this way, so we could have like 2 different columns. So of course, then they will be named under way 1, way 2, different ways. And then you will have instead of 8 different sets, we will have only 4 sets. So 4 rows, 2 columns. And this is 1 column, 8 rows, right? So this is called a two-way set associative cache. So then, of course, the direct map cache is kind of like one-way set associative cache. So it's also a special example of n-way set associative cache. Instead of having n ways, you have only one way. You have only one way, right? So two-way set associative cache, you have a little bit more flexibility. So for example, if you map to, if this piece of data have to be mapped to the set 1, then you could have 2 different blocks to select from. If this piece of data has to be mapped to set 2, you have 2 different blocks to select from. For a direct mapped cache, the mapping location is actually fixed. The mapping location is actually fixed. So for this particular example, suppose we still have the 32-bit address, and then remember right now we only have 4 sites. We only have 4 sets. So instead of using 3 bits to determine the set index, we only need to use 2 bits. We only need to use 2 bits because 2 bits is enough for me to represent 4 different rows, the index for the set, 4 different sets, right? 2 bits is enough to represent 4 different site location. So the set index only costs 2 bits, And remember that the lower 2 bits, their lowest 2 bits, they're always 0, and then plus those 2 bits, then together, then we will need 32 minus 2 minus 2, which is 28 bits as our tag, because for a direct map cache, then you could save 3 bits plus the 2 lowest one. But for a two-way set associative cache, then you can only save 2 bits plus the lowest 2, because you will have to spend 1 more bit. You will have to spend 1 more bit for your tag. So for the tag, the size of the tag is actually 28. It's actually 28. But how can we use this? So you may get a little bit confused about the figure here, right? So how can you use this? Remember that you have 2 different things. You can have 2 different blocks, 2 different blocks for one set. So suppose I have an address, and then I could determine which set it will map to. But after you determine which set, using the set index, then you could either take, suppose it maps to set 1, and you will have 2 separate blocks in set 1, and then you can select any of them. You can select either this one, the first one, or the second one, way 0 or way 1. So you can put it in one of them, and it doesn't really matter. Okay? And later on, when you have another piece of data, suppose it will map to set 1 again. Suppose they have the same set index. And then if the second block is empty, if the second block is empty, then you could put it into the second block. If the first block is empty, then you could put it into the first block. But suppose later on you have the third address still mapped to set 1, then you have to kick 1 out and then put the new things in it. So you have two different blocks. You have two different blocks to hold things maps to the same set index. And how can we use this? So this is like how we do the mapping, right? And if you have an address to read from, so for a given 32-bit address, I will first check which set it should map to using the 2-bit set index. And using the 2-bit set index, then I could determine which row I should look at, And after I fix that row, then I will first check if there are anything inside of those row. And remember, there are two different locations in this row, 2 blocks in this row. So I have to check the valid bit for both the way0 and the way1, both way0 and way1. So the valid bit will be borrowed first of all, so will be checked first of all. So suppose the valid bit is 0, so suppose the way1 valid bit is 0 and the way0 valid bit is 1, then you don't actually want to compare the tag of your way1, because if this is 0, then the AND gate will give you a 0, then the hit 1 will be 0. Then you don't want to worry about way1, then you only need to check way0, right? Then you only need to check way0. Suppose you have the valid bit of way0 is 1. And so on. So the same thing for way1. The same thing for way1. So if you have way0's valid bit is 0, so any valid bit is 0, then you don't want to worry about that particular way. So that column you don't need to check. You do not need to check. And suppose I would like to check from they can both be 1, of course. So you can have both of them equal to 1. And then the next step will be check the tag, because you don't actually know where is the data you want, right? Where is the data? It could be placed in way0, it could be placed in way1. So you have to check the tag, compare the address, if this is the data I want, if the data I want is actually stored in the cache or not. So I have to compare the tag. So by check the tag, which is 28 bits, so I have to compare the 28 bits stored in the cache with my real address, with the address I'm dealing right now, right? So I have to compare the 28 bits, two of them, I have to compare two of them, the 28 bits stored in the cache with the target address I'm trying to read right now, with the target address I'm dealing with right now. And suppose they're equal. If you got an equal here, or you could get an equal here. You could either get an equal here, or you could get either equal here. So you can only have one. You can only have one of them is true. Okay? And suppose it is inside of the way0. And then you will have 1 times 1, which gave you 1. So your hit 1 will be 0, your hit 0 will be 1. And as long as one of them is true, then your hit will be true. As long as one of them is true, then your hit will be true, right? So you cannot have both of them true, because one piece of data can only be placed in one location. So you will not copy it twice. You do not want to copy it twice, of course. So if you have the hit, and then according to the hit is 1, and the hit 1 tells you if this hit comes from the first way1 or way0. If this hit comes from way1 or way0. If hit 1 is 0, that actually means the data is coming from way0 instead of way1. The data is actually coming from way0 instead of way1. And then you know where to select that piece of data. So this is a multiplexer. This is a mux. Helping to select, from like kind of like one channel inside of the inside of the multiple weights, inside of the multiple weights of the current set, So this is how we use the n-way set associative cache, And then you may ask, what's the benefit here, right? So instead of doing a direct map cache and you do a n-way set associative cache, so you do not want to have each set only include one tiny block, so you can have each set include many different blocks, and each block that belongs to a particular way, and then you have to compare, if you have 2 ways, then you have to compare 2 of them. If you have 3 ways, you have to compare 3 things. If you have 4 ways, then you have to compare 4 different things, right? So after you fix the set location, and you have to search everything in that set. So what's the benefit here? Remember that the biggest problem for direct map cache is we do not want multiple address. They share the same set index. So for this particular example, if we have multiple blocks in one set, so one set can map to more. One set could actually map to more different blocks. Could have different blocks. So, and then this will help us to solve the previous example, the problem we saw just now. So if you have the address 4 and 24, because they all map to the same, many different addresses, they all map to the same set. And suppose I use my 2-way set associative cache with the same capacity, try to run this piece of program again. And then I will have to again do the analysis of how the address 4 and address 24, where they will be mapped to inside of the cache storage. Remember that the address 4, the 32-bit address 4, should look like this. And the 32-bit address 24 So the 240. Right. So this is the address 4, this is the address 24. And lower 2 bits, we don't need to worry. Lower 2 bits, we do not need to worry because they're always 0. And remember, if I use 2-way set associative cache with 4 different sets, so the set number here is 4, so I will need 2 bits to represent the set index. So both my address 4 and address 24, they will map to set 1. However, the first time I see the address 4, I will put it in one block, in the first block of my set 1. And then I see the address 24, and I will put that piece of data in the second block. So another way, so I will put it in way 1 of set 1. And then I repeat this program the second time. So I will see 4 again, which is actually inside of the set 1. So I will have a hit. So the first loop, I will have 2 miss because they are originally not inside of the memory cache. They're not inside of the cache memory. And the third time I do the load, so this is the loop, first time and the second time of the loop. So my third load. So this is the first load, the second load, the third load. The third load here is trying to load the address number 4. So the number 4 is actually inside of the cache. So I will have a hit. And the fourth load here, I will have a hit again. And when I loop for the third time, they are still there. So I will have a hit. When I loop for the fourth time, I will have hit. So if you are looping this piece of program for 5 times, so what is the miss rate here? So you only have the first 2 load are miss and everything else are hit. So the miss rate here is only 20%. The miss rate here is only 20%. The miss rate here is only 20%. However, if you use the direct map cache with the same capacity, then the miss rate will be 100%. The miss rate will be 100%. And then you may have the question, well, does that mean I should always increase the number of ways? So, I can do many ways, and I don't want to do, so many sides. So instead of using so many sides, maybe I just grow horizontally. If I can grow horizontally more and more, then this will avoid the conflict sharing the same set index. That will help me to avoid the conflict of sharing the same set index. So of course you can do that, right? However, remember, the more way you have, the bigger n you have. So we call this n-way set associative. The bigger n way you have, the bigger n, the more complex circuit you will have. The bigger n you want, then the more complex circuit you have. Remember, for each column we have, then we will duplicate the tag. We have to duplicate the tag. We have to duplicate you will have to have a tag and a valid bit for each block. And then of course for each way, and then you need to have a comparison circuit. And suppose this number is huge. The extreme case will be you want a fully associative cache, and then you really only have one set. If you have only one set, and then this number will become the maximum number. So the n is how many blocks you have, then you will have, like this. How many blocks you have only, then how many columns you will have. So the set, the way number n, the number of way will equals the number of block. So how many data I want to store, then you will have how many ways. You will have how many ways, right? And so this is called fully associative cache. So you really have just one single set. You really just have one single set, only one row, but many columns, So the problem will be this circuit will become super complex, because you have a lot comparison circuit, and this multiplexer will be super complex as well. So this will be expensive to implement, and it is almost impossible. So, and again, for a 8 block cache, so if I want to do one-way set associative, which is called direct map cache, and it will look like this. So you will have 8 different rows, 8 different blocks, and one set equals one row, one set equals one row, one set equals one block, one set equals one block. And if I want to do two-way set associative, so I will only have 4 different rows, 4 different sets. So for the direct map cache, then one block is one set. For a two-way set associative, I will have 4 sets. But each set has 2 blocks. And for a 4-way set associative cache, then I will have 2 sets. And each set will have 4 blocks. Right? 4 blocks. So a 8-way set associative cache is actually the fully set associative cache. Is the fully associative cache. And then you only have one set. And you will have all the blocks belongs to the same set. And if you want to read anything from this cache, then you have to search all the different locations. So you have to search all the blocks, all the different locations, right? Because you don't actually know where it will map to. So you have to search all the different blocks and compare each of them. So in reality, what people select for an efficient design, so it's hard to determine. So for different company, different consideration. So they have, and for different application, they will have different focus. So this is always hard to do, and it is of course a trade-off. Of course, there's certain trade-off you have to do according to how much money you want to spend and how efficient you want to be. And the direct map cache is not usually implemented, and the fully set associative cache is never implemented. It's never implemented. So of course, it will be n-way set associative cache, but how many ways you want is hard to answer. It's hard to answer, okay? So we will look at more examples in the next video. And I will stop here for this video.